experiment, after we did our experiment, this is our class tallies for our frequency of these different amounts of liberal, different political views versus your gender. Okay, so let's figure this out now. We first want to know what percent of the class, so if you have your calculator, or if you're just smart like that, what percent of the class are girls with political views? So what am I talking about there? But who are girls with liberal views? 1 out of 21. Good, because it's what percent of the class. Okay, good. So then that ended up being our 4.8. We'll just keep it in 1 decimal percent. Good. What percent of the liberals are girls? Yes, 100, because 1 is liberal out of 1, and that's 100%. Okay. What percent of the liberals, so how many liberals are there? 1 liberal, and what percent of those are girls? Okay, what percent of the girls, so girls there's 12, what percent of the girls are liberals? So is that 1 out of 12? Okay. So what do we got? Okay, 8.3. All right. What is the marginal distribution of gender? So what does that mean? Okay, so marginal distribution means what are these values that occurred in the margin? Okay, so I would say this. I would say my male marginal distribution is 9 out of 21. So my male distribution is 42.9%. Okay? My female then should be the opposite of that, from 100%. So they would be 57.1%. Okay. What's the marginal distribution of political views? So that would be this area here. That would be from that margin. So I would have to have one for liberals, and that would be 1 out of what? 1 out of 21. Okay. How about our moderate? That would have been 8 out of 21. Okay. So that would mean that our conservative percent would be 12 out of 21. And it needs to add up to 100, so I got 41.9. Did I do that wrong? I got okay. Because I did 38.1 plus 4.8. Oh, hold on a second. That doesn't seem right. Yeah. Huh. Wow. That's amazing. Look at that. 42.9, and then I did the answer minus 1, and it gives me that. Interesting. Okay. Man, my calculator just gave me a wrong answer, didn't it? I don't know. Okay. What? I know, which is 100%. Oh, which is just 1. I should have told it to subtract 100, shouldn't I? So my calculator did do the right thing. It's just, okay, what is it? 57 point what? Okay. You're like, whatever. Okay. So now if you're ever sad, you can just play this recording back and get my laugh on that. Okay, here we go. Okay. Now, okay. Here we go. And Trevor is so politely not saying, no, Ms. McClellan, you really are an idiot. All you do is just subtract 1. Okay. Conditional distribution. Here we go. Conditional distribution. Let's talk about that. Whew. Conditional distribution is getting the percentage of something based on another trait. It's conditional on another trait. So we want to find the conditional distribution of political preference conditional on being a particular gender. And in this case, it would be male. So how many of our males were liberal? Okay, and I'm going to go ahead and put the relative frequency in here. So that was our 0%. How many of our males were moderate? One out of 9, okay. So there's 9, oh, here it is. Correct, so 1 out of 9. So that's 11.1%. And our conservative males were 8 out of 9, which is 88 should be 8%, but we'll do 9 so that it'll rounded, so that's fine. So, of course, we get a total of 100%. I mean, we had 9 people, 9 males. Okay. So what is our conditional distribution? What is our political preference conditional on being female? So what are our liberal females? 1 out of 12, which, what was that? 4.8 or something? Oh, that's our 8.3. Okay. I'm a math teacher, you know. Moderate was what? 7 out of 12, which is 58.3. Okay. And then our conservative would be the rest of it, 4 out of 12, which is a 33.3, but we're going to say 33.4 so that it totals up to all 12, that is 100%. Okay. So what is the conditional relative distribution among gender among conservatives? What is the condition? Oh, see here it's just asking relative frequency, which we already kind of did, of gender among conservatives. So for male, our conservatives were 88.9%. For females, our conservatives were 33.4%. Okay. All right, now here is the whole shebang. The reason that we are doing this section is to determine independence of 2 things. The book does a really good job of another example of this. It does a good job of the Titanic, so I want you to make sure that you read that part in the book. What it poses a question about is the people that lived and died on the Titanic, was that independent of their class? Or did the percentage of people live, if they were a different class, more likely to live versus, another class? Okay, so the book does a good discussion on that. So there you go. I want you to make sure that you enjoy that part of it. But look, if these conditional, let's define this. If the conditional distributions are the same, we would conclude that the variables are not associated and that they are independent. So let me explain. Up here, if my percentage of liberals was the same as for males, was the same as my percentage for females, then I would conclude that being liberal or being male or female has nothing to do with the fact that you're liberal, or being liberal has nothing to do with the fact that you're a female. But look at how we were quite a bit off here. Look at this difference in conservative. So if I said to somebody these percentages, and then I said, okay, I'm going to put male name in here, you're more likely then to pick a what? A conservative, right? Because it's more likely if I was to say a male, then you would be more likely to be a conservative than any other. So they're tied, then as opposed to a female and being a conservative. So therefore, are gender and political views independent of each other in this class? Or are they related? They are related. Are gender and political views independent? And that I would say no. That according to our data, our political view depends on your gender. Okay, because I wouldn't say your gender depends on your political view, right? Okay. Don't know. I mean, I got to think about that one. If you had two that it was less concrete, I don't think you're stating necessarily that one is depending on the other. You're just saying that they're not independent of each other. So you can tell that they're related. Yes. Probably like, yeah, probably like pretty close, like decimals off, but pretty close to being the same. Okay? All right. So let's go on. Here's another way. Here's an easy way to tell. Sometimes we put things in bar charts. So we had like 0 liberals in males, and then we had, what, 1 moderate. So I'd like have a little bitty teeny tiny part of a bar, and that's our moderate. And then the rest of them were all conservative. Whereas our bar chart for the female would look like this. We had 1 that was a liberal, 7, and I'm just kind of 7 that were moderate, and 4, so that should be smaller, that were conservative. I didn't quite draw those perfectly, but if it was independent, these bar charts would look the same because the relative frequency would be the same, but they are not. It's very easy to tell from a bar chart that they're not the same. Okay, next concept, the area principle. Area principle means that it should look like the right amount of area, and you better watch the way you draw it or else it might get skewed. For instance, this looks pretty, but when you turn it like that, artistically, it's going to skew the visual size of these pieces, so this will actually look like a lot less than it really is. Okay, a really good example of that is this right here. Can you explain what's wrong with this graph here? Yeah, hello, 50% is not exactly half. So you can see that the area principle is not being met because we would have to have, show it at 50%, and because of the way that it is angled, it doesn't look like it's 50%. All right, and that's all it's saying. The book does have a good picture to represent that, about the Titanic and ships and size of ships and stuff that way. Let's go on to the last concept, which is Simpsons Paradox. And where have we heard of Simpsons Paradox before? Yes, in our summer articles. So what I want to do, though, is I really actually liked the example in the summer articles better. So we're going to just nix your last page of your notes, and we're going to go to our summer articles page, if I can pull that up, which you don't have, but I'm just going to demonstrate it up here for you. Okay. Yes, with the physics class. Okay, so let's see if I can explain this for you really quickly. Here we go. Okay, let's see. These are people. Let's go through these tables, and hopefully through the course of these tables, it'll be clear about Simpsons Paradox. Okay. And in fact, I had these tables on your summer articles quiz. Okay, here is high school students that took physics or didn't take physics, but they went into an engineering program. And so the physics that they took in engineering was pretty tough. Physical engineering is engineering physics is a whole lot more difficult than, say, a liberal arts physics. This is a calculus-based physics, whereas you can just do mostly geometry stuff with that and be fine. Okay? So because these courses are significantly different, the paradox occurs, but let's walk through it. Okay. So this is students in high school that went into the really hard physics class. If they had high school physics, they averaged an 80. If they had not had high school physics, they got a 70. So they had an improvement. Good? In the course. They did better in the course because they had high school physics. Okay? How about these? These are students that went into a liberal arts program. Well, 5 of them took high school physics, Not as many, because if they're thinking they're going into music or, you know, art or something that they don't think that they have to have something as intense as engineering, they might not consider taking this in high school. Okay? So those that took high school physics just really blew the top off and did very well in their liberal arts physics, because it's what? As compared to this one is easier as compared to the engineering program. Okay. And if they didn't, then they did less. They still had an improvement if they took high school physics. Okay, so in both of these, it states that you would be better off if you took high school physics. Correct. Do you follow that? Okay. But look at what happens when we combine those two data sets together. And this is where Simpsons Paradox occurs. When I combine these two data sets together, this would happen. These are the students who took high school physics. So I lumped them all together. These ones took high school physics, and it says that there, but I'm just making it really clear. These took high school physics, 50 here, 5 here, but because a larger chunk of them were in the harder engineering class, what does it do to this average? Makes it lower. Okay? These are students that did not take high school physics, and so there was only 5 of them in the harder course and 50 of them in the liberal arts course, which was easier. So look, more of them had a what? Higher score. So therefore, the overall average ends up being higher. So a non-educated person or somebody who's trying to skew your understanding would say, hey, look, you will make a higher grade if you do not take high school physics. Right here, look, you're going to make a better grade if you do not take high school physics when you go into college. Okay? So that is Simpsons Paradox, because when we combined the data tables together, it got skewed and bent because of the change in the difficulty levels from up here. Question? Okay. So that's the last part that you want to make sure that you get in your Chapter 3.